I want to keep going with our coin and die experiment to see what's going to happen with empirical and classical probabilities in the long run. All right, so we're going to repeat a third and a fourth time. We're actually going to do two of these. So let me toss. Oh, I got a heads and a 2 this time. Oh, I was so close. Heads and 2. And actually, I'll do it again. I'll do a fourth time. Up, tails and 3. So I'll do that one in blue. So this was my fourth, and this was my third. Okay. So when I did this with a class, I sometimes actually keep going. We do 5, 6 trials. But I just stopped with 4 for us. So we got 0. Suppose in my class we had 0 out of 20 trials. And then for the fourth trial, we had 3 out of 20. Okay, so what's the empirical probability of tossing H1 for the third round and the fourth round? Well, for the third round, it was 0 out of 20, which is 0. And for the fourth round, it was 3 out of 20, which is 0.15, in case you're interested. Okay, so now let's put it all together. How many trials of the experiment were there in total? Okay, well, we had 4 trials, right? And then how many? Oh, and I'm going to cross off 3 and say 4. So we did 4 trials. And again, usually in class I do 4 or 5 or 6. Okay, so all in total, let's think. The first trial we had, I've got to grab my sheet. We had 1. Then we had 2, then 0, then 3. So 1 plus 2 plus 0 plus 3 gives us 6 total. Oh, I'm not going to do that in black. I'm going to do this in blue. There we go. 6 H1s. Now, how many trials were there? Well, that's easier to figure because we did 20 for the first, 20 for the second, and so on, which makes 80 trials. So the empirical probability overall from the total results would be 6 divided by 80, which is 0.075. Just so you can see it. 6 out of 80. Yep, 0.075. I didn't lie to you. There you have it. All right, so what's going to keep happening, right? So in the long run, if the class repeats this over and over and over and you tally the results, right? Instead of looking at the individuals, if you look at the overall results for the group, what do we expect to happen to the empirical probability of H1? Well, let's consider for a second. So we had our first trial, which was 1 out of 20, which was 0.05. Our second trial was 2 out of 20, which was 0.10. Our third trial was 0 out of 20, which is 0. And our fourth trial was 3 out of 20, which is 0.15. And then we tallied these together, and we got 6, well, actually, let me start with this. So what they're saying is, suppose we tally along the way. Suppose instead of doing it at the end, so you say, hey, take these two, right? If you take these two, that's 3 out of 40, which is 0.075. Then take these 3. That would be 3 out of 60, which is 0.05. Now take these 4 trials. It was 6 out of 80, which was 0.075 again. Right? So what they're saying is, hey, suppose you, instead of looking at each trial individually, you start looking at how these 2, and then these 3, and then these 4, and then these 5, right? Because you'd have a 5th trial, which would be some number out of 20, and you would keep going. So what do we expect to have happen in the long run? That's what they're asking. So if we say, hey, start comparing these numbers, what's going to occur? And hopefully you can see what's happening, right? These all vary because they're empirical, but what's going to happen is they're going to get closer and closer, right? This value over here, this last value, whatever it is, the probability of H1 overall for all the trials put together will get closer and closer to the classical probability of 0.083. Right? That's what's going to happen. It's, real life is messy. Real life, as I said in the last video, it's messy. There's a lot of randomness, but the values aren't far away from what they should be, right? So what's going to happen in the long run is you're going to wobble. You're going to, get some high values and get some low values. There's going to be randomness. But in the end, in the long run, that 0.083 is what's going to win out. Right? That's going to be the long-term probability. And so this is locked in stone, right? So this is locked in, and these guys waver because real life is messy, right? Because real life has randomness to it. I guess another way of saying that is that, as we talked about, all these probabilities waver and move around a bit because real life is messy and random. But in the long run, which is the long run is that one at the end. Let me kind of highlight it in green. The long run is this guy, right? This overall probability, right? This is the overall probability of H1, the last one that we do, right? It's not the last one here, it's the last one if we tally all of the trials that we've done. So when we tally all the trials we've done, that last tally will approach the classical probability, right? So that overall empirical probability will approach the classical probability. It's going to get closer and closer and closer to it. The more trials we do, the closer it's going to get. Now, if you're thinking, whoa, that sounds heavy, and it is, and that is called the law of large numbers. Right? It has its own little thing. So I actually did this as a simulation because, of course, we can't toss 10,000 times, but that's how many times we tossed, right? So this is trials right here, the number of tosses. So there's 10,000 trials, and I simulated it with a computer program because, of course, we can't do this by hand. It would take us too long. I just added that note. I mean, we talked about that when we talked about simulations. You do simulations to save yourself time and money. When I do this in a class, even just doing it 4 times or so, it takes us, a good 10 minutes or so to tally all the results and get all the feedback, etc. So does this simulation support our answer? So you can see, look, it started off wobbling around, right? So we had a 100% probability because they must have gotten H1 right off the bat. And then it goes this way and this way and this way. But you can see that in the long run, it's getting closer and closer to that value of 0.083. Just a little bit under 1. So does this simulation support our answer? Yes, the simulation supports our thinking. Because, and you can see it kind of happens pretty quickly. After about 1,000 tosses or so, the probability of H1 gets closer and closer to the classical probability of 0.083. And you can see it's wavering. It gets a little high right there and then a little low. So it's not perfect, but it's real close to that 0.083, right? Over here, definitely. So as the number of tosses increases, as we move to the right on the graph, we're getting closer and closer to that 0.083 line. That is the law of large numbers. The law of large numbers says that as the probability experiment is repeated over and over again. The proportion of times that a given event occurs, which is the empirical probability, right, which is messy and varies a bit, right, from problem to problem or trial to trial, will approach the classical probability. There's no such thing as the law of averages, though. You say, because of this, then, definitely an H1 is going to happen. It doesn't work like that. An H1 is likely to happen in the long run 0.083 of the time, right? 8.3% of the time. But that's what that means. Now, what does this mean for the gambling industry? Okay. So gambling games have a lot of variability to them, right? So gambling games have a lot of variability. That's where the fun comes from people. Variability and randomness involved. That's one of the reasons people play, right? If it was going to be you're going to lose every time, then nobody would play that. But people play it because it's got variability. It's got randomness. Sometimes you're up, sometimes you're down. But that means that players can get up. Because of that variability and randomness, then sometimes players are up, quote unquote. They're ahead. They've got more money in their pocket than they came in with, right? So casinos need to keep gamblers there, especially gamblers that are up. If you get down a significant amount, for example, they might come over and offer you something like a free show or a free stay at the hotel, etc., because they want to keep you there, right? So they want to keep you inside the casino and playing because in the long run, the law of large numbers, in the long run, if a gambler stays, they will lose because the classical probability will win. Right? The classical probability wins in the long run, always. Right? It's not that you can't be up, right? You're up, right? You go up. See this little wavering there? You can do that. But in the end, it will slump back down to what it should be. That is just the nature of gambling. All right. So what do casinos do? So casinos have no windows. Right? Go into a casino. They don't have light, not natural light. They have no windows, no clocks. They have neon lights to confuse your brain, right? So you don't know what time of day it is. They have cheap food, free drinks a lot of the time. And then if you're winning or losing a certain amount, they'll come over and offer you free drinks. They'll offer you, money and things to stay. They have very maze-like architecture. I've been so lost sometimes in a casino. Like, where am I? Because they want you to get lost in the warren of, machines and things like that. So you don't really know where you are. In Michigan, for a long time, COVID has affected this a bit, but they were exempt from the no smoking laws because they don't want you to have to go outside and smoke outside and then think about your choices and see what time of day it is, right? They don't want you to have to see daylight. And there's more, right? I'm just going to put ... right? There's lots of things. So if you're going to gamble responsibly, I mean, this is not an exhaustive list, but if you're going to go to a casino, you want to gamble responsibly. Me personally, I've been to casinos a few times for shows, but I don't gamble, so because I just can't handle it. It's not for me. But so you want to go with a plan. We're going to go see this show. We're going to get a meal here. We're going to do this here. You have a plan, a schedule, and you stick to it. You have friends, right? You don't want to go gamble alone. That's a recipe for disaster. etc. You have time that with that schedule comes time limits. We will only gamble for this amount of time and that's it, right? We will not exceed that. Um, take only what you can afford to lose. Never take your cards. Always leave an emergency amount of money, like an emergency 20, in the car. And that's not for you to go gamble with. I've actually known, because I'm related to a state trooper, and he's actually run into people that are leaving casinos and they run out of gas and they didn't have enough money to drive home. In Michigan, right? That's happened. And then if you get up, walk away. Just walk away when you are up, right? Go see a show, go watch a movie, go do something else. So if you get up, if you are riding that variability and randomness and you get to this point where you're up by a bit, walk away. I did that one time. I've gambled very few times, and I was waiting for a friend, and I was in a nickel slot machine, and I put in a few nickels, and I won $20, and I just got up and walked away. I literally walked out of the casino. I just waited for my friend outside. I figured I was up. I had enough money to buy a pizza. I was good. So do that, right? Do not stay and keep trying to win. And if you're down, definitely walk away. Don't try to win back. It's not going to work. That's just the beginning. Of course, you can look up online lots of tips for gambling responsibly and ways to be smart about it if you choose to go to a casino and gamble, which of course you do not have to do. Again, I've only been in a casino a few times in my life. I've gambled that one time, and one other time I played nickel slots and I lost like $5, and that was it. That's all I've ever gambled, because it's just not for me.